Okay, really quick, before we move on to some more problems on this handout, I do want to address a mistake that I made in the last problem. I even checked for mistakes and I missed it. So what I did is I wrote the function f of x incorrectly. F of x was equal to x squared plus 4, and for some reason I wrote minus 4 here. So let me just change that. This should be plus 4, and that changes this to plus 12 when I simplify. So sorry about that mistake. Now we can go ahead and move on. So that's all I wanted to look at in section B. Let's take a look at section C now, where we're dealing with the topic of functions. Okay, you spend a lot of time talking about functions in algebra, and you know, from then onward, functions are really a central topic in all of mathematics. We're dealing with functions. Okay, so what I want to do is a few problems concerning these guys, and I think I'm going to focus on just 2 of these problems in section C. I would like to look at problem 3 because this involves something that we are going to be spending a lot of time looking at in calculus, and I also want to do problem number 6. Okay, so let's start with problem number 3. Given f of x equals 1 over x, simplify the difference quotient, f of x plus h minus f of x all over h. Difference quotients are something you may have learned about already back in pre-calculus or college algebra, or wherever you would have learned that prior to this class. And we're going to define them again in calculus because they represent something really, really important in calculus. But for our purposes, this is going to be treated just like a normal algebraic simplification problem. Okay, so again, that's our function right there. This is problem C3. And we are given f of x equals 1 over x, okay? And we're asked to evaluate that difference quotient, or simplify it. Now notice the difference quotient involves an f of x plus h. And h we're just understanding to be some number that we're not stating specifically what it is, but it's showing up in this first part of this expression. So what does f of x plus h mean? All that means is that I'm taking my function f of x and I'm plugging x plus h in for the input, which shows up in my denominator. This is the same as 1 over x plus h, okay? So now we have our difference quotient, which looks like this: f of x plus h minus f of x all over h. And I'm going to use my results from up here to start plugging some things in. So f of x plus h is the same as 1 over x plus h. And then minus f of x, that's like minus 1 over x, okay? All over h. Now the goal here is to simplify. And as you're going to see in calculus, when we start doing a lot of work with these things, by simplify, there's a specific way to know that you have simplified this. And the way that we're going to know that is, first of all, notice that we're dealing with a big quotient here. If you were to plug a 0 in for h, you want this denominator to not end up equaling 0. So I want to simplify this to the point where I have a denominator down here where if I were to plug 0 in for h, I get a non-zero denominator. And right now, that wouldn't happen. If I plugged 0 in for this h, that is going to equal 0 down here. Another way of thinking about that is we want this h down here to somehow cancel out in the process of simplification. So in this case, the natural way to simplify an expression like this is to eliminate these denominators. This is what we call a complex rational expression. We have rational expressions within a larger rational expression. And I'm going to use a trick that you need to be very, very comfortable with in calculus: multiplying by an expression that's equal to 1. So in this case, notice if I were to multiply these two denominators together, x times x plus h, that's what we would call the least common denominator of these two rational expressions. And if I multiply this by x times x plus h over itself, that's the equivalent of multiplying this expression by 1. This is the same thing as 1. And we know that that's okay to do because multiplying something by 1 doesn't change it, okay? But it does offer a way of simplifying things. So now Think about what would happen if I took this x times x plus h and distributed it to each of these terms. Something will cancel in each of those products. So for example, x times x plus h times 1 over x plus h, I'm going to see the x plus h's cancel out and just leave me with this x. Okay? Minus, now I need to multiply x times x plus h to this term, but in this case, this x will cancel with that x, leaving me with x minus h. And here, once again, is where you need to be really careful. Some people will be tempted to write this, minus x plus h, and you will be wrong if you do that. Because what you're doing is you're only actually subtracting the first term of that expression. This has to be in parentheses. I say that, I've said it a couple of times now, because this is one of the more common mistakes I see in these types of problems, even in calculus, where you should not be having that problem anymore. Down in the denominator, I'm not going to multiply this x in or anything. It's going to benefit me to have everything kind of in factored form. So multiplying these two denominators together would just look like h, x plus h, okay? Now up on the top, I could distribute this minus in, and notice I'll end up with an x minus x up here. Those x's cancel, they zero out, and then I'm left with negative h over hx, x plus h. And that's great because now I can get the cancellation that I said we wanted. These two h's can cancel each other out, and I'm left with negative 1 over x times x plus h. Now remember what I said, you know that you have simplified this sufficiently if I can plug a 0 in for h and get some non-zero expression in my denominator. So if I were to plug a 0 in for h here, then this would become x times x, or x squared. That's a non-zero expression. And no, I'm not thinking of what would happen if I plug a 0 in for x. I just mean we want something that doesn't look like the number 0 showing up down there. So this is where I stop. That's now simplified sufficiently, okay? Okay, let's go ahead and move on to number 6. Now I'm going to fix this on the handout before I send it out to you guys, but my text got split by the picture. That's a mistake. We can still read it, but I'll make it look better on the handout before you get it. So what this says is shown below is the graph of f, some function f, and we're asked to evaluate f of 2. Now this is what we call a composite function. Oftentimes you'll see something like f of g of x or g of f of x or something similar. And that's essentially the same thing that we're working with here, except we're composing the function f with itself. And with a problem like this, you want to work from the inside out. So first of all, I have enough space to write this problem here. I'm just going to do this on this. F of 2. I start on the inside. What is f of 2? Well, I don't have an algebraic rule to work with for this function. I only have a graph, but that's enough because f of 2 would be found by plugging 2 into our function. If I found 2 on my x-axis, it's down here. And looking at my graph, I have a point here. Remember that this circle is thought of as a whole. There's not a point at that specific little circle. So when I'm looking for what f of 2 is equal to, I have to find where the point is, and that's up here. Notice that the y-coordinate of that point is 4. So that tells me that f of 2 equals 4. Therefore, this is the same thing as f of 4. But how do I determine what f of 4 is equal to? Well, I do it the same way. 4 is down here. If I plug 4 into my function, I get 1. And that's it. Now that's a considerably quicker and simpler problem than the ones we've done previously, but I put this in here because when we're working with functions in calculus, which functions are the backbone of everything that we do in calculus, we're dealing with functions, we have to be comfortable looking at functions and extracting information from them with multiple different ways of representing those functions. In fact, if you read chapter 1 of our book, which we're not covering, I believe that the author says that functions can be represented in one of four common ways. There's verbal, which means you're given some written description in words of the function. There is numerical, which is where you're given like a table of values corresponding to ordered pairs in that function. There's graphical, where you're given the graph of a function like what we have here. And then there's algebraic, or sometimes I think they call it analytic, where you're given something like this, f of x equals some algebraic expression. All of those are valid ways of representing functions, and we need to be comfortable working with all of those different representations and pulling information out of them. So in this case, we're working with the graphical representation of a function, even though we don't have an algebraic rule ready to be used. Okay? All right. That's it for section C. Let's take a look at section D. We're dealing with trigonometry here. And in this one, I think I'm just going to do two problems. I would like to do, let's see, I think I'd like to do problem 1 and problem 4. Okay? We use lots and lots and lots of trigonometry in calculus. It's a big, big part of calculus. And one of the things that you're going to really have to have a good handle on is trigonometric identities. Okay? So in this first problem, we're told that we have an angle theta, and we're specifically told that it's in the first quadrant of the unit circle. And we're given this information about it. Sine of theta is equal to 4/5. Okay? We're asked to evaluate sine of 2 theta. Now, this, if you remember from trigonometry, this should ring a bell. Sine of 2 theta can be expressed differently using a double angle formula. So this is going to be problem D1. Okay, 1 second here. Okay, problem D1. And we're asked to find sine of 2 theta. From trigonometry, this is equal to 2 times sine of theta cosine of theta. Okay? Notice we're given some of that information already. We're told what sine of theta is. It's equal to 4/5. So I could put a 4/5 in here, but we're not told what cosine of theta is. Fortunately, there is enough information here to determine what cosine of theta is. And you can approach this in a couple of different ways. You can construct a right triangle in the first quadrant to figure out what cosine of theta is. Or another way, you can use the Pythagorean identity, which is the approach I'm going to use. So here's the Pythagorean identity. It says sine squared of theta plus cosine squared of theta is equal to 1 for any value theta. Now notice we're given... We know one of these. Sine of theta is equal to 4/5. Okay? So that's like saying 4/5 squared plus cosine squared of theta is equal to 1. Now 4/5 squared is equal to 16/25. If I subtract that from 1, I get cosine squared of theta equals 9/25. Let's take square roots of both sides. Cosine of theta would then be equal to plus or minus 3/5. Plus or minus because I need that after taking the square root of both sides. Now, it can't be both of those. It's either positive 3/5 or negative 3/5. And that's where this little bit of information comes into play. We're told that theta is in the first quadrant. And what we know about our trigonometric functions is that sine, cosine, tangent, secant, cosecant, cotangent, all of those trigonometric functions are positive in the first quadrant. So that allows me to narrow this down and say that it's not negative 3/5. This would have to be positive 3/5. Okay? So now I have enough information to get my answer. Sine of 2 theta is equal to 2 sine of theta cosine of theta, which in our case is equal to 2 times sine, which is 4/5, times cosine, which we just found is 3/5. 4 times 3 is 12, times 2 is 24, over 5 times 5 is 25. I have 24/25 here as my answer. Okay? So that's how we go about a problem like that. Now let's take a look at number 4. solving a trigonometric equation. So here I want to solve cosine squared of x plus sine squared of x equals -1. And we're also told that we're looking for solutions between 0 and 2 pi, not including 2 pi. This little extra condition here is there because generally when we're solving trigonometric equations, we get an infinite number of solutions. And that happens because these functions in here are periodic. We get a repetitive pattern that results in infinitely many solutions oftentimes. But usually we don't want to, in a lot of contexts, we don't care about those infinitely many solutions. We really just want the ones that are showing up within that first revolution of our unit circle. So that's what this condition here is saying. Let's go ahead and try solving this. D4. We have cosine squared of x plus sine of x equals -1. Now, when solving trigonometric equations, there's a few strategies that help. One thing that's helpful is trying to put all of my trigonometric functions in terms of the same function. That's not always what you want to do, but in this case, it would help a lot. And what I'm going to do is, once again, use my Pythagorean identity. Cosine squared is the same thing as 1 minus sine squared of x plus sine of x equals -1. So where I originally had a combination of a sine and a cosine showing up, I now only have sines showing up. Next thing I want to do is move everything over to one side so I can get a 0 on the other side. If I moved all of this stuff over here, I would get 0 equals sine squared of x minus sine of x minus 2, okay? And once again, we have a quadratic equation in disguise. So this is another place where variable substitution would be really helpful. Let u equal sine of x. Now I'm going to say this really quick. So if you have had enough practice with these, you may very well be able to move to the factoring step without having to make a variable substitution. You may be comfortable just factoring this as is. So you don't have to do this variable substitution thing here. I'm doing it, one, because some people will benefit from writing this out first, but also because we use variable substitutions a great deal once we get to integration at the end of this class. And so this is kind of helping you warm up to that idea. Anyways, moving on, we have 0 equals, making our substitutions, this becomes u squared minus u minus 2. Can we factor that? Let's see. 0 is going to equal, u minus 2, u plus 1. Now let's substitute that sine of x back in there. 0 is equal to sine of x minus, 2 times sine of x plus 1. From our zero product property, we know that this implies that sine of x minus 2 equals 0, but that's the same thing as this. Sine of x equals 2, or sine of x equals -1. Now, once again, you have to know your functions. Because again, if you are too mechanical with how you solve equations, you will forget this next step. The function sine of x has a relatively small range. The range of sine of x is the closed interval from -1 to +1. What that means is that this is impossible. You can only get values between -1 and +1 inclusive when using the sine function. 2 is outside of that range. So this doesn't give us any solutions. That means we can focus strictly on this guy. Sine of x equals -1. And now here's where you need to know your unit circle. Sine of x is equal to -1 for only one value of x within one revolution of the unit circle. And that occurs at x equals 3 pi over 2. Okay? Now I'm going to point something else out here, which is, again, very important in calculus. You notice that I wrote my solution in radians as opposed to degrees. You may have done this problem, and if you're more comfortable with degrees, you may have written 270 degrees. And for this particular problem, that's not that big of a deal. Except, technically, you would be wrong because I did put this condition here. X has to lie between 0 and 2 pi. That right away implies that we're looking for radian measure, not degrees. But kind of the bigger point I want to make here is that in calculus, with very few exceptions, anytime a trigonometric function shows up, we are pretty much always going to assume that all angles are measured using radians. And the reason for that is extremely, extremely important. Once we get to chapter 3 and we start talking about derivatives of functions, we're going to derive a rule for how to take the derivative of a sine function and a cosine function, as well as the other 4 trig functions. Those rules do not work if you don't measure your angles in radians. So it's extremely important for the purpose of calculus that we think in terms of radians, okay? With, again, just a few exceptions. All right. That's all I wanted to do for the trigonometry section. Now we move on to modeling, which is our last section. Why can't I pick this page up? There we go. Okay. Modeling problems are going to become really, really important when we get to chapter 4. And a little bit in chapter 3, but mostly chapter 4 when we're doing something called optimization. And these are all applications. These are like word problems. When we talk about modeling or mathematical modeling, in this context, what we're trying to do is take a description of a problem that's given to us and come up with a function that represents that situation. So in all 5 of these problems, the goal here is to come up with a function, okay? And I'm going to do 3 problems here. These are really great problems, and you're going to see probably all of them in one form or another when we get to chapter 4. But I want to start with number 1. So number 1 says, an open-top box with a square base has a volume of 10 cubic meters. And we're asked to find a function s of x, representing the combined area of the base in square meters and the sides in terms of the length of an edge of the base x. Okay, that s of x is like a surface area function. So this might seem a little bit daunting at first, but let's break it down into the information that we're given. So first of all, we're doing E1 here. These problems are often really great problems to draw a picture for. We're usually wanting to draw a picture. So we're told that we have a box with an open top. Okay, and we're also told that it has a square base. Okay, so here's my box. It's really important that we keep in mind that the base is a square. And we're told to think of one of the edges of that square base as having a length of x. Now notice if this is equal to x because the base is square, that will also be equal to x. We're not told anything about the height of this box. So I'm going to assign a new quantity there. I'm going to call it h for height. Okay, now let's go back to the information that we're given. First sentence says, the open-top box has a square base, which we accounted for, and a volume of 10 cubic meters. How do you compute the volume of a box? Well, the volume of a box is just base times width, or sorry, the length times the width times the height. So our volume, which is equal to 10, is equal to the area of the base, which is x squared, times the height, h. Okay? Now that's not the answer, right? Because that doesn't give us the surface area. So let's look at the surface area next. I want a function s of x, which gives me the combined area of all of the surfaces of this box. Now because it's an open top box, there's not a top base to consider here. But the bottom base, being a square with a side length of x, has an area of x squared. The side faces of all of these, or of this box, are rectangles whose dimensions are x and h. That means the area of any one of these rectangular sides is x times h. And because there are 4 of them in total, adding everything up would give me 4xh. Okay? Now, it looks like I've answered my question because I found a function s of x. But I haven't actually answered it yet because s of x means we should be looking at a function of one variable, a function of x. And over here, I'm seeing two variables. I'm seeing x's, but I'm also seeing an h. So the key in problems like this is to find a way to eliminate any extra variables in that function, h in this case. And in order to do that, we use this previous information that we've been given. We called this thing a constraint. So how do I use this constraint? Well, notice if I were to solve this for h, I would have h equals 10 over x squared. Okay? And what that does is that gives me a quantity or an expression in terms of x that I can substitute for this h. So having that now, I can write s of x equals x squared plus 4x times 10 over x squared. And technically I could leave it that way, but it's not simplified, so it's better to do a little bit of work simplifying it. S of x is equal to x squared. This x will cancel with one of those x's, giving me an x in the denominator. 4 times 10 is 40, so I have 40 over x. That's a simpler version of that function. Okay? Now again, just to remind ourselves of what we just found. We found a function where if we were to find the length of one of the sides of this square base, just that one length, we could plug it into this function, and the end result would give us the entire surface area of that box, which takes into account the fact that we don't have a top on that box. Okay? So that's the first and honestly the easiest of the problems that we're going to be dealing with. I have two more problems from the modeling section that I would like to do, but I think I'm actually going to do them in a part 3 since this video is starting to get kind of long.